Welcome to a presentation on accelerating SOC verification with SOX Verifier using a software-driven approach. In contrast to block and unit-level designs, SOC designs have an embedded CPU core which changes the verification landscape significantly. It's not enough to verify if the hardware works, but also verify the software's integration with hardware. In SOC verification, in addition to providing stimulus at the interfaces, software running on the embedded core is needed to simulate the DUT from inside. Hence, this can be termed as software-driven verification. An effective SOC verification requires coordination between test bench and DUT. As of now, there are no methodologies and very minimal automation for test creation. If you look at the current practice, verification starts with running basic tests and few driver-level scenarios to confirm if the IP transacts data, at which stage RTL is handed for validation. In the validation stage, the entire focus shifts to getting a commercial OS booted on the SoC. Any issues found during the process is either masked by software or fed back to verification. Each incremental step in fixing such issues leads closer to OS bring-up. As part of this process, much of the driver and application code gets developed, refined, and fine-tuned. So what ails current practice? At the end of the validation process, there are no guarantees that all hardware-software issues have been explored. This means that complex hardware-software issues still lurk, and the reasons could be hardware-software tests require coordination of DUT and test bench event activity. They are laborious and effort-intensive to create. The lack of automation tools also means that multiple use cases of the same scenario remain untested. Lack of any methodology during test development results in limited reuse. This means that existing scenarios cannot be combined to increase concurrency in the system. Lack of knowledge of how an OS would sequence calls to an IP results in orthogonal tests. The lack of a controllable verification test bench makes control and debugging of issues effort-intensive. The end result, with no means to test complex hardware-software interactions, such issues remain hidden, and therefore much needs to be achieved at validation time. So what does SOX Verifier solution offer? SOX Verifier solution is based on three concepts: automation, methodology, and language. Automation is based on pre-built and auto-generation of test bench and DUT components. The generated test bench and software components makes it easy to coordinate and control hardware-software scenarios, thereby boosting productivity and comprehensiveness. With scenarios comprising of software, it makes it important to have a methodology for test development. SOX Verifier provides a structured test development methodology based on extensible base classes. This enables scenario combination, reuse, and use case exploration. Methodology is drawn from UVM and OVM and is verification friendly. Users can spec verification intent to SOX Verifier in a subset of system Verilog language constructs. Higher level language primitives like fork, mailboxes, semaphores, etc. provide the necessary abstraction to think in the problem domain. Programming language interface to C is also provided to reuse legacy code. Using SOX Verifier approach, users can spec driver level or application level scenarios with ease. Coordinating test bench DUT event activity is much easier due to pre-built and generated components. The ability to reuse scenarios and combine them enables comprehensive testing of complex hardware-software issues, resulting in higher bugs exposed early and having higher confidence in OS bring-up activities. SOX Verifier automation solution comprises of SOX VIP test bench component and SOX OS software component. SOX OS is a C library which handles all channel communication details and scheduling for the test application. Depending upon the scenario intent, SOX OS can span from a simple command interpreter to a multiple thread scheduler. The SOX VIP architecture is similar to traditional VIP and is OVM UVM compliant. SOX VIP and SOX OS form the infrastructure to enable coordination and control of scenarios. In SOX verifier, hardware-software verification intent is specified in system Verilog-like language. The scenario intent is translated into C test software and SOX OS components. Relevant portions of this intent is translated into test bench components which plug with the SOX VIP. The top-level generated sequence runs on SOX VIP, which coordinates and controls test bench DUT activity. Memory channels are created in a portion of system memory to exchange data between SOX VIP and SOX OS. User-defined data like sequence items and tool and user-defined data flow through these channels. The management of the channels is done by SOX VIP and SOX OS and is transparent to the user. To summarize the feature set, SOX verifier generates all the repetitive and boilerplate OVM or UVM code for test bench components. Depending upon scenario combination, multi or single-threaded code is auto-generated. For an effective software-driven verification, SOX verifier provides all the means to coordinate test bench and DUT event activity. This makes it possible for software to launch sequence on VIPs. Software can also raise or drop objections while executing. In addition, there are predefined OVM or UVM events on which test bench can attach callbacks. Users can also define their events or software coverage points. SOX verifier provides a structured methodology for scenario development. Leaf-level scenarios can be encapsulated hierarchically to form complex scenarios. This results in bottom-up development. A structured test development also ensures scenario combination, which results in maximum reuse and top-down development during later phases. The methodology is very similar to OVM and UVM and is verification friendly. It's based on a set of 4 extensible base classes. These base classes are layered as shown and serve different purpose. At the bottom is SOX resource base class, which forms the device abstraction layer. The SOX scenario represents the test application layer, or how to use multiple resources for a test scenario. The SOX sequence is all about how to run and combine scenarios or sequences. The SOX sequence item captures the constraints of a scenario under which it should execute. Let us see SOX verifier in action. The verification intent we have taken is a driver level scenario where Ethernet IP alone is functional. In this scenario, the software drivers need to be tested for different use cases, where each use case varies packet length and the number of packets received. The intent has been arrived at keeping in mind the simulation throughput of the verification platform and the demo duration. For the purpose of demo, we have taken a mock SoC, which is a Xilinx Microblaze 32-bit RISC CPU with AXI4 bus and Xilinx IPs. The IP of interest is the Ethernet MAC and its internal DMA block. The SoC has a 64 KB of internal SRAM and 128 MB of DRAM. The SOX VIP channels are present in the DRAM block. The Ethernet MAC has been interfaced with a VIP acting as an active file. As mentioned earlier, verification intent to SOX verifier is specified in a subset of system Verilog, using a set of 4 base classes. The SOX resource represents the base class which captures the programming content related to an IP. In this example, Ethernet RX DMA channel represents a sub-resource which captures all the programming resource sequences related to one DMA channel. The parent Ethernet MAC class models the MAC and its programming details and encapsulates the Ethernet RX DMA channel object. The SOX sequence item class captures the constraint information. In SOX verifier methodology, each scenario class is tied to a SOX sequence item. In this example, the Ethernet packet item class constrains the packet length and packet count variable as per the following rules. Sequence item of type Ethernet packet item are randomized and channeled to the software running on the CPU. The SOX OS scheduler executes the scenario thread on the CPU and provides sequence item objects of type Ethernet packet item for every run of the scenario. At the end of each run, SOX OS scheduler sends the sequence item back to the SOX VIP for scoreboarding and coverage activities. The SOX scenario base class is intended to represent test application. Scenarios can be leaf level or hierarchically structured through instantiations. Scenarios usually would involve one or more objects of SOX resource. The base SOX scenario class provides predefined virtual tasks or functions which resemble the phases of the UVM. For example, init task gets called first, followed by run task, and followed by the finite task. In this scenario, named ETH_RX_SCN, SOX sequence item class type of ETH_PKT_item has been associated. The intent is to receive PKT_count number of packets of length PKT_len. For this scenario to function, it needs to coordinate with the test bench to launch a VIP sequence. The path of the instance on which the sequence has to be launched is also provided. In addition, the DUT software code takes an objection at the beginning of the scenario and drops the objection at the end of the scenario. In SOX verifier methodology, execution or combining of scenario is decoupled from the scenario itself. The SOX sequence base class controls the execution of a scenario. For example, the sequence ETH_TX_SEQ intends to execute the scenario ETH_RX_SCN thrice with randomized objects of sequence item type ETH packet item. Multiple scenarios can be combined using fork join concepts within a SOX sequence. Similarly, multiple SOX sequences can also be combined to form higher level sequences. All of this intent is provided to SOX verifier, which generates OVM or UVM compliant test bench components. It also generates the C test software equivalent. These generated components have been integrated into the mock SOC setup. At the end of simulation, we can see that the execution of the scenario ETH_RX_SCN for 3 sequence items. The waveform shows the interrupt lines of the microblaze CPU, the Ethernet DMA engine, and the Ethernet packet data transmission lines. SOX verifier executes the scenario ETH_RX_SCN with different values as determined by the sequence item ETH_PKT item. All of the test bench and DUT coordination have been transparent to the user and controlled by the SOX VIP and SOX OS combination. SOX verifier automatically samples coverage of SOX sequence item objects which go between test bench and DUT. In here, we can see the random variables PKT_length and PKT_count being sampled, and their cross coverage has also been sampled. Finally, to summarize, SOX verifier provides all the necessary automation in terms of generating test bench and software components, thereby enabling testing of complex hardware-software interactions. Methodology ensures scenario combination resulting in top-down development and maximum reuse. All this enables studying and verifying complex interactions early for a comprehensive verification, thereby having higher confidence during validation and OS bring-up activities.